Really great day of talks, kicking off by Anna. Our finale today is a little bit different in the sense that Scott Morrison from ANU is going to be giving a talk on temporal algebras and Kovanov homology, and it will be joint with the other group, the operator algebra group, so you'll see lots of other unfamiliar faces in the room. And just to remind you, because we are such a photogenic crowd, not only does the Newton want your individual photo, for which they're willing to bribe you with a coffee cup of the kind Josh has, but also we'll have a group photo later on, before or after a coffee, so everyone's suitably chipper. Anyway, just to forewarn you. Thanks very much, Anna, for starting off today.
Thank you very much for the invitation. I had only one time, and I'm very much enjoying my stay here. So I'm going to talk about slopes, color links, and the eta function, which is a joint work with Degtyarev and Vincent. So let me start either defining you for the first time or reminding you what's this eta function, which was defined by Kojima and Yamazaki in the late 70s. And the setting is the following. You want a link, which it has to be a two-component link in S3. And you ask for this link to be algebraically split, meaning that the two components have trivial linking number. So in this setting, you consider the complement in S3 of K2, and then you look at the infinite cyclic cover of this that I'm going to call my x2 tilde. And now the microphone. And here we've got the covering translation given by tau. And so this is the infinite cyclic. And downstairs, in the complement of K2, we still have our not K1. And I'm going to consider L1, which is just going to be a preferred longitude, a zero pushed off of K1. And these two lift. And I'm going to take nearby lifts. If not, it doesn't work. So I fix where do I lift K1, and then I take the L1 to the corresponding place to some closed curves in here, because the linking is zero. So when you lift, you actually see the curve upstairs, and that's kind of the essential part where this hypothesis is needed here. So now, as you all are aware of, H1 of X2 is as a ZT module distortion and the order is given by the Alexander polynomial of K2. So what happens is that the Alexander polynomial that I'm going to call delta 2 of t annihilates the homology, always considered as a ZT module, which will be important in everything that follows. And this means that if I consider delta 2 of t and then take this multiple of the L1 seen as a homology class, then this has to be the boundary of some S, which is a two-chain. Yes, because that's zero in homology. So now we have all the ingredients we need to define the eta function, which is the following. So the eta function of the link L that has two components, but that we evaluate in just one variable, is given by 1 over delta 2 of t, the Alexander polynomial of the component that we are forgetting. And since I am going to talk in a minute about links, then you will see that I am divided by this Alexander polynomial. In the case of knots, they are always non-zero, so I'm in a safe place, but then I will always have to add this hypothesis of the Alexander polynomial of some link non-being zero for being able to divide. And then this is the standard way when you work with this equivariant coverings is to do things like this. So now I'm going to intersect the two chain with all the translates of the lift of my longitude, and then I'm going to recall where do I have the intersection. This is just the intersection in the covering. So this is a 2 cycle, this is a 1 cycle. I just see how many times do they intersect, recall that number, which is an integer, and get this function. So what's interesting about this function is, of course, its properties. So let me just give you some of them. The first thing is that the eta function of a link L is a top concordance invariant. So if you have two pairs of two-component links and there are cylinders embedded in S3 cross I that join these two, then the eta functions need to coincide. Then perhaps you are not very familiar with the eta function, but you've heard about Cochrane in '85 did some has established a series of derived invariants. The setting is the same. You take a two-component link with linking number 0, and then you associate what are called these beta series of invariants, which are the beta 1, beta 2, beta 3. They are all integer numbers. And this series of derived invariants is related to the Kojima eta function in a very explicit way, and it's that they constitute a generating function for the eta function. So if you do this little change of variable, you call x 1 minus t times 1 minus t minus 1, then it turns out that the eta function in the variable t equals, well, let me write it like this. The eta function of L equals the sum from e equals to 1 to infinity of beta I of L xi, which this benefits both sides, because when in Cochrane's series of derived invariants, he studied other type of properties, for example, that these beta I are behave well with band sum for boundary links, so that's something that then you get for the eta invariant for free, and the fact that the eta invariants are topological invariants gives you the topological invariants, concordance invariants for the Cochrane derived series. And very recently, like there's a preprint this year that revisited this Cochrane invariant from Conant, Schneiderman, and Teichner and relates them to Whitney towers. And there's a last little remark on this Kojima eta function that I want us to have present today, and it's the relationship between it and the Alexander polynomial. And this was developed by Taek Jin, that I've been twice corrected on the spelling of this name. I hope I got it right this time. In the paper published, it's written like this. And I was told it was not like that. So hopefully this time I get it right. So this is in the 87, and we need some a normalization of the Alexander polynomials. So if I consider delta et equals to delta et minus 1, so I get the symmetric versions, delta e meaning the polynomial for k1 and for k2. And then I consider the two-variable polynomial of t1, t2, L being the link. And then I want this normalized in such a way that I can pull out a factor t minus 1, a factor t2 minus 1, and then this times a function, which this is symmetric. It's always possible to normalize things like this. So if you put yourself in this setting, then the eta function happens to have this particularly nice form, or at least particularly nicely related to more common invariants if you want. It's either plus or minus, and in the article it says, if you read the article you can figure out the sign that should fit. And yes. So it's 1 minus t, 1 minus t minus 1, then the g gets a 1 and a t, and then you divide by the delta 2 of t. So let me just comment a second on this, because we will see it again. The eta function is a quotient of Alexander polynomials. Let me remind you that Alexander polynomials are not concordance invariant. So it's kind of remarkable, if you want, that a quotient of them is actually a concordance invariant. And the special part is played in here from the generalization that I'm going to talk about by K1. So we are studying K1 in the complement of K2. And this k1, so to speak, disappears and gets a 1 in this formula, and then we divide by what has, by the Alexander polynomial of the covering we are considering. Okay, so let me now change completely the setting and what I'm talking about, and tell you about this other part of the title, which implies these colored links and slopes. So the idea will be that I want to generalize this Kojima eta function, but I'm not going to give you a function on t variables to start with, but I'm going to define you a number associated to a link. And then this number associated to a link, when you evaluate, there will be an evaluation that gives you that this number, this slope, it's just evaluating this function in a particular vector. Okay, so let me start little by little. So slopes and colored links.
So when you say concordance invariant, concordance invariant as a link, or if you keep k1 or k2 fixed? You keep k2 fixed and then you look at concordance of a non.
No, as a pair, as a link. It's cylinders that take k1 and k2.
Both can change.
Hmm?
Both can change.
Yes. So what's a colored link? I am going to consider links of this type. K is going to be a particular component, and then L can have as many components as it wants. And this K will always be playing this role of this K1. And it's going to be one mu colored. And I am going, just because of the applications that I have in mind for afterwards, I'm going just to consider S instead of S3, which is going to be a Z homology sphere. For everything I say, except for the last bit, you just can imagine that it's S3. It's just a technical detail and two more lines in each proof, but it's nothing important. So what do I mean by a one mu colored link? I think that instead of giving you the definition, I am just going to draw a picture. So it's just a way and a language for codifying the variables, if you want. So imagine I have such a link. The one is always going to refer that to my k, that it's going always to have a special color. It always goes by himself. So this is k. This is a 1, 2 colored link. Because it has this blue and red. And so if I want to think about ku, what I would think is that I have k union a red link of 3 components and a white link and a blue link of 1 component. And so this division corresponds to these 5 knots and that link. And this division is just, you have to think of the colors as the variables in the invariants.
K is a knot.
Sorry?
K is a knot.
K is always a knot. Yes, yeah, always. That's why I will always keep the K for him. So what do I mean by colors, variables in the invariants? This is all very simple. It's just that it's the language that helps to do this. I can consider K union L, and I consider the Alexander polynomial in one variable. What does that mean? You take a Seifert surface with 5 boundary components, and then you do the usual computation. You can also consider the Alexander polynomial of this link in 5 variables, 1 for each component, and that would mean that you just work with several Seifert surfaces, one with each one boundary component. And one can think, okay, instead of having this dichotomy, let me just put myself in a context in which I can do whatever I want. So here, what I am considering, if I am looking at invariants or whatnot and how to compute them, I am considering these 3 red components together and the blue one separately. So in the 1-2 colored version, I would be looking at an Alexander polynomial of k union L on the variables t, which is always going to be t, no subindex for my knot, and then I would have a t1 in red and a t2 in blue. So it's just a way of organizing the information. There's a whole theory behind it. It's well known, for example, for the signatures of the Alexander polynomial, what happens if you have a maximal coloring, and then you just put the same color and things like that. So there's a whole language developed around it. So to define the slope, I need colored links to start with, and then I need a character. So the second ingredient will be a character that I'm normally going to call omega, and this character, it just takes an element of the pi1 of the complement of L. Let me just go back to here. L is playing the same role as K2. So K is still in here. And I am going to go to the complex numbers. And I am not going to use every possible character because I am interested in the role that K plays in this link. So to get some information on K and to take it from the theory of the coverings and twisted homology, I need to see K upstairs. So I'm going to say that a character is admissible, and all the characters that I'm going to use are like this. So if I forget the word admissible, it should be there. If when I see K as a loop here and an element of H1, it goes to 1. I need it to be trivial on K in such a way that I can see K when I look at the covering. So I'm going to be extremely concrete. So let me just, this is all that one needs to develop the theory, but I want to get very much hands-on. So I'm going to see which is abelian, so I can factor everything through homology because I am not as brave as Stefan Friedel, so I am going to go to somewhere that is abelian. So the H1 of S minus L, it's generated by the meridians. So M1, I'm going to keep the notation for this example, okay? M1 to M4 in this case, because I've got 1, 2, 3, and 4 components that I'm taking away. Now, I am working in this colored setting, so I don't want to consider the M1, M2, and M4 different, because I want them to have the same color. So the coloring gives me a further factoring that I'm going to go to, just let me keep this for only now, T1 and T2. So whatever I do with my meridians, I just want them to respect the coloring. So in here, M1, M2, and M4 go to T1, and M3 goes to T2. And then I can go back there. So any character needs to factor through all this. So which means that any, like if I can consider the group of characters, and I take one character here, omega, this that was defined on the level of pi 1, and I can just think of it as a tuple given by the color. I remind you that mu is the number of colors. So how do I do this? I associate to omega this omega 1 to omega mu, where this is just the image of T1. Okay, so I am going to consider all, whenever I'm going to work with the character, instead of working with omega, I'm going to work with a mu tuple of elements in C, which will kind of be very, very concrete for what we are going to do. So again, I have this knot that sits in the complement that sits in S minus L. I have a character. This defines a covering just by looking at the kernel, and I am going to look at my knot when it lifts, and then I want to get some information from there. And the standard technique to do so is to look at these twisted homology groups. Or homology with local system of coefficients, or I even think it's not the only two names that I've heard for that. And it's exactly the construction that Stefan was telling us yesterday about. So you start considering the chain complex of the universal cover of S minus L as a set P module. And then once you have this, so this is the cellular complex, and then I want to consider the cellular complex of S minus L, but twisted by my character. Oh, sorry, let me just introduce this notation, which is just some sort of reminder. Via this character, I can see C as a set pi module. So if this is pi, the group, then this character allows me to view C as a set P module. So I can use it in my construction to tensor. This is going to make the same job as the Neumann algebra the other day. So this is kind of the very baby kind of case. And just to remind me, the notation that I'm going to use for this is C omega. So this is just notation. It's just the complex numbers. The only thing that I'm reminding myself is that it has this action that comes from that character. So how am I going to define this chain complex? This is just the chain complex that I started with, the one of the universal cover with this structure as a set P module, tensored over set P with this copy of C that I endow with this structure. And then I just considered, as of definition, that whenever I will write this, this means the homology of this guy. Okay? So this is really the same construction as we had the other day, but for most of the applications I have in mind and the settings that I'm going to deal with, it's way too much. Like, you can't really understand it in a very easier, perhaps more geometrical or pictorial way. So let me just, for the sake of clarity and perhaps for the ones of you that might not have worked with this, do a very baby example that will hopefully illustrate a bit what's the importance of this. So of course these need not be in the realm of 3 manifolds. It's a construction that you can do whenever you have a manifold and a character, then you consider the universal cover and do the same thing. So let us just, for the fun of it, compute, let us consider S1, and let me give you like the exercises that Stefan gave us the other day, but like we are going to work it out. So I'm going to give you a character on H1 of S1, and I am going to go to the cyclic group of 4 elements sitting in C star. So I'm going to take my generator, L, and I'm going to send it to the complex number I. So why am I doing this? Because I want to, it's really the same algebraic setting, but I am just going to make it very, very concrete. So I have S1 here, and my character omega defines a covering of order 4. And let me say that here the homology is generated by this loop that I'm going to call L, and here the homology is generated by this loop that I'm going to call L. And here we've got the covering transformation tau, which is going to give us the action of pi 1. When you go one element of pi 1, you go 1 here, so that's the action. So we want to compute the first homology group of S1 twisted by this very concrete character. So one should start doing all this construction, but of course the algebra here is so easy that what happens? That this module is flat over this one, so instead of computing the homology here, you can compute the homology first and then do the tensoring. And moreover, this here, if you just think a bit about it and sit down, is telling you that you are just actually computing the homology of this covering. More or less. So it is actually turns out to be, in this case, it's the H1 of S1 tilde, let me call it to this S1, the one given by the covering, with coefficient in Z tensored over Z C4 Z, which is less scary perhaps than all that, but I want to kind of really go up to the end to see what is this group. So if I get an element in here, I need to get a generator, an element. Here the group is Z. I said that it was generated by L, so let me take L and tensor it with a complex number, Z. So now I am going to see how does this action work. So I'm going to consider tau of L, tensor Z. But now tau of L, if I see L as my generator, it's just a quarter of a turn, so it stays the same. So this is, so L is tau of L, there's no difference, and this tau, thanks to the quotient, to the tensoring, it's the same thing as L times IZ, So this is how one needs to think about these things in very concrete terms. So now what happens that from here you deduce that L tensor Z1 minus I is 0. But this is no matter which complex number that is non-zero, you can write it like that. So you have just shown that this more or less scary group that you had at the beginning is a trivial group. Okay, so the homology of with twisted coefficients of this S1 is trivial. And that is going to be, apparently I didn't know this, but it was Viro who remarked the importance of these things at the beginning, apparently. And so let me just write it as a remark of Viro that will be kind of essential in what is coming now. If you have a torus and you have a character that is non-trivial, then what's going to happen is that the homology of the torus with twisted with this character, and also the cohomology, all this twisted version of homology just works perfectly well, it's going to be trivial. So one can think in these very concrete terms when one has a character of finite order. You can always go to the covering of finite order that corresponds and think of this twisted homology as the homology modulo the action. If something is invariant by the action, then it will be killed. So whenever you have something like this, it won't be there. Okay. So let us, after this very little and hopefully not too boring introduction to how do these things work in concretely, let me go back to my colored links and admissible characters and give you the definition of the slope. We now have all the ingredients to understand how it works. So I am going to consider the boundary of a tubular neighborhood of my node K. I remind you K is this special component when I restrict my character to it, the character is trivial. And I am going to consider the H1 of this with twisted coefficients by my character. But by way all that I have said, if you restrict to K, then you are trivial. So then your homology is non-trivial. And in fact, since you are twisting with the identity, you are just doing nothing. So this group is really C2 generator by your preferred meridian and longitude of the tube of K. Okay, it's just a two-dimensional vector space. Now, I'm going to try to get information on this looking at S minus L. So I am going to see what happens when I get the inclusion of this into the H1 of S minus K union L, again twisted by my character. So I've got a torus, which is a boundary component of this 3 manifold that has many boundary components. And I want to look at the kernel of this. So I have some H1. I probably wrote something wrong then. I remind you that the character is defined on S minus L. So the meridian of K goes to 0 just because it doesn't see the other ones. And I am asking K to go to 0. So if the linking were 0, then you have it for free and every character is admissible. But I am really restricting to this case, okay? So this is, let me call it V, just to make it less scary, V for vector space. It's a vector space of dimension 0, 1, or 2, depending on this being injective or not. So I'm going to look at this, and the definition is the following. If this vector space is generated by one single vector, so if the kernel has dimension 1, and let me say that it's generated by this, so A and B are just two complex number up to scalars, then the slope of k union L at omega, and again, this, I know omega was my character. What do I mean by at omega? At omega, I mean I'm understanding my character in this dual way as an mu tuple of complex numbers. Is given by the following expression. Never found a better notation for this. Minus a over b, which is a complex number order infinity. So whenever you have this setting, you need a not in a link and a character that it's admissible. The only thing that you require is that it vanishes on your k. Then you can compute this number. And you get this slope. So, of course, no one wants a definition that starts with an if something happened. Because what if this were never the case? So then everything would be a bit empty. But let me just start with some very easy remarks. So we've more or less established what happens when you take omega or the conjugate, or it's just a bit of algebraic manipulation. But the important thing here will be that if omega, that I'm, to remind you, I'm considering it as a mu tuple of numbers, is unitary. And what I mean by this is that the modulus of each one is 1. So instead of going to the whole of C, I am concentrating in S1. Then the slope is well defined. What I mean by well defined every time that I will say this is that that kernel is actually one-dimensional. And moreover, it's real. So if you restrict yourself to this set of characters, then you have a well-defined invariant every time, and then you have a real number or infinity. For all the rest of the talk, I will be on this setting. Many of the things that I'm going to say do not need the character to be unitary, but just for the sake of clarity, I'm just not going to make the difference every time. And if I have to confess something, in my head, they are not only unitary, but they are always of finite, like they are always rational numbers of finite order. We've gone through quite a bit of trouble to extend it to non-rational characters, which I suppose that the algebra behind makes sense, but already in the setting of finite order, the theory gives nice results. So this another little comment that goes in line with Jake's comment before is that if you have a one mu colored link with the property that the linking number between each colored set and k is 0, then every character is admissible. Just because in that case you have that necessarily k is sent to 1. So if you have in your head this Kojima story, you see everything more or less fits in the same pattern. The only thing is that we are not working with a function, but directly with this omega, which allows us on the one hand, and I think the most interesting part is that there are more admissible characters than the case linking equals to 0. You can have an admissible character when the linking is non-zero, so then you can hope to get the information that is hidden in this construction for this new set of links that would not fit in this pattern. But of course, I need to get to the end, which is how do we put together this slope with this Kojima function. So to do that, I need to start with to give you a very kind of immediate multivariable version of this construction. So let me just write it down. So if you want a multivariable eta function, of course, with this definition, the problem is that then the properties that you want are not so straightforward. But you can define it like this. So if you have a k union L, which is a one mu colored link, and I am going to take L a preferred longitude, And I'm going to take a character, but this time I'm not going to send it to C, but to the group G, which is T1, T mu, the abelian group in these T variables. And I am going to send the meridian I, which is any meridian of the colored component I, to Ti. So now I am really mimicking the T part of this version instead of the concrete valued part. And now I need this. This is very bad. Let me continue here. I am actually going to rewrite this blackboard with T1 T mu instead of T1 of T. So, okay, if I am here, what do I need now? So I need this a bit annoying hypothesis that we've been trying to see up to what extent do we need them. So if the Alexander polynomial of the link is non-zero, and the link being the part without k. And moreover, the linking between, and this time this is absolutely essential, k and li is 0 for all I. Because this will guarantee that under phi, k goes to 1. And it's the only way to guarantee it. So here we need it. Then you can see L. This L was my preferred longitude of k as an element of H1 of S minus L with coefficients in this module, this ring. And here this is torsion again. The order being delta L. So again, as before, you can consider delta L times the class of L, and this will be the boundary of a two-chain. And then you can define your multivariable eta function on these mu variables as 1 over delta L times the, let me do it like this, equivariant intersection. Of course, you need to prove that it does not depend on the choice of u. I am actually hiding a little bit. You need not use the whole delta L, just something that annihilates L, and then you just have to show that it does not depend on the multiple that you've chosen. But this is a very straightforward way of just getting your eta function into variables. So the result that I wanted to present, now that you've got all the ingredients here, is the following. So the theorem, which is together with Alex Degtyarev, Vincent, Florens, and myself, is that if the Alexander polynomial of this link is different from 0, then the slope at omega is finite for all admissible omega such that delta L evaluated in omega is different from 0. Take into account that the polynomial being non-zero is one thing, and then I am specifying a character in this case because the slope is just the value somewhere, and I wanted that in that value my polynomial be non-zero also. And moreover, and here is where I do where the link with the slope comes in, if the link that I started with has a property that Lik equals 0 for all I, then the value of the eta function of k union L in this omega coincides with the slope at omega. So wherever the slope, wherever the eta function makes sense, then it coincides with the number that we are associating, and the number that we are proposing has many more chances of being computed in other cases. So that's one of the results. The other one, it's going to kind of reassure that what we are doing actually seems to be correct and makes sense. And it's another statement that relates this number that we have found, this slope, with the, instead of the Alexander polynomial, we are going to relate it to the Conway polynomial. Just, of course, they are all renormalizations of each other, but it turns out that for the way the proof works, it was more convenient to have the Conway polynomial in it. So the other statement that we propose is the following, the same three authors. Which is, if you consider the Conway polynomial, that this is just a change of variable with respect to the Alexander polynomial, and I'm going to call just for the fun the derivative with respect of t of the Conway polynomial of k union L. I remind you that t was a variable that I was always specifying for k. So then, for any admissible omega, I remind you, an omega being admissible just means that it's suitable for our construction. K goes to 1, so we can see k in the covering. Then what happens is that k over L omega equals, on the one hand, this derivative evaluated in 1 square root of omega, and that just means you take the tuple and you take some normalization for that to make sense. Oops, no, it's always the Conway one, sorry. If the Conway polynomial is different from 0, and it will be infinite if this one is 0 and the numerator is non-zero. And if not, like just in freshman calculus, you just have no idea what happens, and then case by case you have to resolve this indeterminacy of 0 over 0. So if you take a look to this side, it's really kind of the exact thing that one would expect if things made sense. We have this Alexander polynomial of the whole link on top, evaluated at 1 in the variable that corresponds to our k, and we are quotienting by the Alexander polynomial, well, Conway in that case, of the part L, that it's just the part that we were using here, k2, to determine the covering. So I would like to give you some of the ideas of the proof, but let me just the key thing is to play between the Conway polynomial and the Reidemeister torsion. Of the 3-manifold S minus k union L. So I'm just going to wave hand because it's a technical proof, but it's really very hands-on. What you do is you just want to compute what is all this about. You have a particular component in the boundary, which is a torus that comes from your knot, and you want, when you lift it to this covering defined by your character, you want to understand how the homology of this sits in the whole piece, because you are trying to understand a kernel. So you just write it down. You say, okay, I put a CW structure in here. After some elementary collapses, you can say that without changing the boundary, it's a 2 complex. So then you start, okay, I take my torus. That is the first thing that I want to have under control. I put a 0 cell there, two 1 cells, and a 2 cell, so I have control there. And then I say, okay, I take the meridians to be the other cells. Then you use the fact that the Euler characteristic of this manifold is 0. So then you have a control on how many 2 cells you have. And then you really write down the whole thing. So you write down the matrices, you compute the Reidemeister torsion by hand, and you see that since you know what's the relationship between the Reidemeister torsion and the Conway polynomial, then you write those down and see that when you specify in your value omega, what you get is this slope. Okay, so I'm not really going to write the details. I don't think it makes too much sense, but just to let you know that there's no hidden machinery behind. It's sit down, write the complex, do the computation, the result comes out.
I don't see how you get the direction of the kernel. Like, what is it? I don't see how that relates to Reidemeister torsion. I can see one can sort of push around things, but I don't quite see. Here is diffusion slope. How does that fit?
Well, the fact I can discuss it with you a bit later if you want. But it's, I'm sure that when you see the computation, you say, okay. It's the point being that you have, you are working with this guy and again with this other one at the same time, and then a quotient of these two gives you that. On the randomizer torsion of, like, you play with this and filling in this component, and then it comes out. Okay, so I am a bit disappointed that what I actually wanted to be kind of the main result of all this, it's not yet quite proved all the details, so let me just put the statement as a work in progress, which we wanted it to be in progress only up until end of January. I suppose that that deadline is already gone, but we'll see. So what we want to show, of course, is that besides this being this way of computing these things and perhaps an easier way or a reasonable way to extending this slope, the eta-invariant, one would want to show that this is a concordance invariant, since the eta-invariant is. So in the two-variable case, it's clear that that has to be the case. So the work in progress is, so perhaps these, I don't really think it's false, but perhaps it needs some fine-tuning in the statement, would be that if you have two colored links, K union L and K prime union L, so that are topologically concordant. And of course you have to decide what does that really mean, if it's the colors that go, like if it's a colored concordance in which they won't be cylinders, they will have multiple ends on one side, perhaps three red things go to a red thing on the other side. So
you don't want cylinders, you want one or what do you want?
I want, yeah, genus, like if these three are red, this is a concordance.
So it's like genus zero.
Yes, genus zero, yes. So if you have such a definition and you have an omega, which is admissible, because if not, nothing makes sense, and we need it to be of prime power order. This again is just the technicalities that we are trying to understand a bit. And we need, again, that the Alexander polynomial needs not to vanish. Perhaps you can work more and also deal with the cases when you have a vanishing and an infinite slope, but that's the thing that at this point we don't know it. Then the conclusion should be that these slopes coincide. That on the one hand, and on the other, of course, you want to make this theory as computational as possible, because if not, like it's much more powerful if you actually can do things. So we are working with a C-complex approach. What are these C-complexes? When you have a colored link, instead of looking into ciphered surfaces, you look to surfaces that have clasps. So perhaps this is a surface that comes from a green link, and then this one comes from a white link, and this is the analogous of a ciphered surface in the context of colored links. So we are trying to give some formulas to compute the slope directly from how do curves behave in this diagram. And so this is for the next time. And in this last 10 minutes, let me just give you one application of the slopes, which is actually, all this work started with us not being very aware of the existence of this Kojima eta-invariant. So it's not that we tried to extend it in any way. We were working on signatures of splice links. It's the same people, it's Degtyarev, Florens, and me. And the problem that we wanted to look at is if you've got a knot and one mu-colored knot in a homology sphere is prime, and you have another copy of this in another sphere, then you can do this operation that is the splice of these two links. So the splice consists of a link L in a homology sphere S. L is just L prime union L prime prime, and this sphere is obtained by taking the complement of k prime in S prime. You take the complement of k prime prime in L prime prime. So you've got two manifolds with one boundary component that is a torus, and you are going to glue them via phi, which gets you the meridian to the longitude and the longitude to the meridian. So when you do this, you get always a homology sphere if you started with homology spheres, and the components k and k prime are no longer in the picture, and you have a new link L in a homology sphere S. And we were trying to understand what is the signature of, like, the goal was to understand the signature of L. How do I write this? The signature of L in terms of the signature of k prime union L prime and the signature of k prime prime union L prime prime. So we spent some time working on this project, and the signatures are invariant related to coverings again if you want, and that can, so if you are familiar with the Tristram-Levin signature, you have a knot k, and then you associate for every root of unity a number which is the signature. I never remember how to do this properly. It's 1 minus omega, the ciphered pairing, plus 1 minus omega conjugate, something like this. No, there's some formula like this to get the signature. So you can do this in a multivariable setting, and then we wanted to understand this relationship, and this omega that appears there also plays the role of a character, as in all this slope business. And we were not able to give the complete formula when the character omega is admissible. Meaning that here, when I do this, then this sigma L is actually sigma L evaluated at some omega. This is sigma k prime union L prime evaluated somewhere and in omega prime. And this is something like sigma of k prime union L prime prime evaluated somewhere and omega prime prime. So this somewhere is exactly, I understand my omega as a character, and I evaluate it in k prime prime, and I put it here. And here, I understand my omega as a character, I evaluate it in k prime, and I put it here. And what happened is that when we were trying to understand this, if this was 1 and this was 1, then we were not able to make the things work. But we were for a long time thinking just that it was our own limitation, that the formula should hold also in that case, but that we just could not figure out the details. And it turns out that no, that we couldn't do it because the formula, the general formula, does not hold in that case. And the general formula does not hold in that case and needs a correction term that comes from the slopes. So let me just write that down very briefly here. And perhaps a word of where does it come from. So if, and I'm in the context of this signature business, okay? If omega is admissible, which in this context, I insist, means that the variable that would go here is a 1 and the variable that would go here is a 1, and those you cannot choose because they are given by how you are gluing. Then what happens is that the signature of my link L, that I remind you is just L prime union L prime prime. So it has kind of some set of omega variables, omega prime here and omega prime prime there, that are from the whole problem established. So if I want to evaluate this in here, then the formula reads it's the sigma of the first part in omega prime plus sigma of the second part in omega prime prime plus a correction term that it's always there and it has nothing to do with the slopes. Okay, this is just this if omega were not admissible and we were in the realm of this other result that we had established for all this, the formula would stop there. And this term is always there. This is just only depends on the linking numbers. Sorry, linking nothing. I'm sorry. It's just the lambda prime would be a vector that recalls the linking number between L prime and K prime, and lambda prime prime between K prime prime and L prime prime. So of course, since I have not introduced anything, it's just the default way of writing it for me. This is a function that we have completely explicitly given. It looks very awful. But it does not depend on the nodes you start with. It just depends on how they link, so you just give the value. So this is the formula in the general case. And the formula, when omega is admissible, then has this following thing. Then you have to understand, since here in this formula there are signatures and signs all the time, SG is going to be the sign of a real number. So the sign of the slope evaluated in omega prime minus, and something that is not completely trivial, the sign of 1 over omega prime prime, no, sorry, KL in omega prime prime minus the slope in omega prime. And this here, it adds up to, it's minus 2, minus 1, 0, 1, or 2. So it's a correction term that comes from here. It's always real. And moreover, it's symmetric, even though it doesn't look like. Meaning that the role played by the double primes and the primes, if you just do all the cases, it's the same. So here it's a first, if you want, application of the slopes. Without them, we would not have this formula. It needs this. And perhaps just for the people that are more familiar with this, just me use my last minutes telling you where do all these slopes come from and what are they doing there. If you think of signatures, you think of 4 manifolds and of cutting them and pasting them. And then the signatures have these formulas. If you glue along the whole boundary, then you have Novikov additivity that tells you it's just one plus the other. And if you don't hold along the whole boundary, then you have Wall's non-additivity theorem. So this is a big 4 manifold, X, and it's divided in 2, x1 and x2. These are 4 manifolds. And they are glued along a part of their boundary. So this is 3-dimensional, this arc is 3-dimensional, and this arc is 3-dimensional, okay? So I've got y1, that it's the boundary of this part, y0 that coincides because it's the gluing part, and y2. And then where you are gluing all these things together is in these 2 dots that, of course, they are disconnected, but they should not, which is a torus. And what Wall tells you is that the signature of X equals the signature of X1 plus the signature of X2 plus a correction term. And the correction term depends, it's a slope. Meaning what? That here you've got your torus, that it's playing the same role as the torus that I had along my K. And I have three manifolds, y1, y0, and y2 where it sits. So I can ask myself, when I twist all these things and do all this business, what's the kernel of this twisted homology of this torus when I look at it in y1, y0, and y2? And those kernels are exactly these slopes, and some sign of the combination of the slopes is what it's going to give you this correction term. So these correction terms that appear here, it's the way that you cook up the signatures that come up in this formula. And that's all I want to tell you.
More questions for Anna?
Why did, when you're looking at these, you always pass to this preferred longitude?
Yes.
Why did you need to do that and instead of just take K instead?
Because I take one is K, that it's, I'm going to intersect K with one surface bounded by K if you want.
Oh, okay. So you just
I want the push off and then just intersect with the surface. Like this cycle that it's upstairs is the one bounded by this other one.
and that the boundary of the two chain
Mm-hmm.
is a that's like a one chain.
Yes, the boundary of.
That lives what I mean.
So I am upstairs, so to say. So I just take a like this curve L, which has just the push off, does not bound, but since it's torsion, then I have to get a multiple. But a multiple is something that involves this covariant transformation. So the coefficient has these t's in it because it's the Alexander polynomial. So that it's the thing that bounds a two chain, that the two chain again lives in H2 of, as I said, t module.
I mean, and the point is that that kind of boundary, in some sense, is the slope. You're recording that as
Yes. Yeah. Yeah.
Well, let's thank Anna again for a great help.
Thank you.